discuss processes in operating systems. So when you create a C code or a Python code, it is actually a passive entity initially. It's just a .c file that you save on your disk, right? So once we compile and execute that passive entity, or what we called a program, then it transforms into an active entity, which is a process. So a process is simply a program in execution. This is the memory layout of a process. So we're gonna have something like a text section where you keep the program itself, right? All the different instructions and lines of codes that you've edited, it stays in the text section. And then the different global variables that you declare in your code will stay in the data section. And then you have the heap and stack sections. So the heap will contain all the dynamically allocated memory that will happen at runtime, and for the stack section it will contain all the temporary things like function parameters, local variables, and so on. So the data and text are both fixed, they do not change at runtime, while the stack and heap are of variable size. So as we said, the process is simply the program itself in execution, so it is active, right? So once we execute your code and it gets loaded into memory and it starts running, then we call it a process. Before that, it is called a program. So bear in mind that one program can actually be transformed into several processes to execute one single program, and we will see how later in this course. So this is an example of a C code right here, and the different sections and where each will belong. So you can think of things like the variables that you declare here, the X and Y, will go into the data section. You can have initialized versus uninitialized sections for the data. The dynamic allocation of memory here will go into the heap, and so on. So a process is identified by the kernel using something called a PCB, process control block. So think of it as the ID or the ID card, right, of the process on the system. It contains the critical information related to that process, things like the process state, which we will talk about next. It contains things like the program counter, which is a simple pointer that points to the next instruction to be executed by the process. And also the PCB will have some important information like CPU registers, some scheduling information, the priority of that process, the different files opened by that process, different memory management informations, and so on. So that's the PCB. So think of this computer system right here, where initially we only have the kernel, and so we only have OS related processes on the system. And then once a user logs in, then a new PCB is created for that user. And then once the user starts interacting with some programs and opens a browser, for example, then a new PCB, right, it is created for that application or for that program, right? And it is coming right from the user's PCB. So to understand more the concept of a PCB in an operating system, think of this analogy where we have the employment agency, right, versus the operating system, which is our context. So the worker in an employment agency is our CPU, each worker has certain jobs to execute, right? And that's our program, which consists of multiple instructions. And each worker has a working location, and in our context, that's the memory. All programs, in order for them to be executed, they have to be loaded into memory. That's where we keep data and instructions. And obviously, to keep track of the worker's status of its job, right? So the corresponding thing in our operating system context is the PCB. That's where we keep the different important attributes of that process to keep track of its progress. And obviously, a worker has multiple resources. In our operating system context, we also provide different data and instructions to operate on as part of the resources allocated to that process. So the different attributes in the PCB have different types. Some of them are integers, like the process state and the CPU state. Others are actually pointers, and also we can have some linked lists there. For instance, a list of the different open files, the different files that this process has opened so far, and linked list of the different resources that this process is using so far, and so on. Coming to the process state, a process can go through different states in its life cycle. It can change from new to running, waiting, ready, and terminated. So initially, a process is created. We do not have any resources allocated to this process just yet, so we say it is in a new state. Once we allocate different resources that this process needs to begin executing, we say that this process is in the ready state. It is waiting for the CPU scheduler to allow it to execute on the CPU. Once the OS scheduler allows it to run on the CPU, then it goes into the running state. So running means it is currently running on CPU. So while running, the process may need access to some extra resources or data. Then the process itself may choose to go into the blocked, or sometimes we call it the waiting state, to wait for those resources to be ready. And then once those resources or data is allocated, then the process is moved back to the ready queue to wait for the scheduler again to allow it to run on the CPU. Sometimes the operating system may choose to suspend some processes from making any progress for one reason or another, and then the process is moved into the suspended state. So in this state, the process is not allowed to make any extra steps or any extra progress. And then once the operating system decides to reactivate that process again, then it depends on the initial state that the process was when it was suspended. So if the process was initially in the running state when it was suspended, once it gets reactivated by the operating system, then it goes back into the ready state again. Now, if it was initially in the waiting stage when it got suspended, then once it gets reactivated again, it goes back to the waiting state again. Because the operating system the reason why the operating system has suspended that process has nothing to do with the resources that the process is waiting for. So the process will go back into this blocked state again to wait for whatever that data it was originally waiting for. So obviously, once the process is done executing, then it moves into the terminated state. So when we talk about scheduling, and we have an entire chapter about CPU scheduling algorithms, it is the job of the CPU scheduler, which is an OS component, to choose which process to execute next on the CPU. Now, the kernel's goal is to always maximize the CPU utilization and keep it always busy and always has a process to execute at a time. Processes come in two main types, I/O bound and CPU bound. With I/O bound, the process tends to spend most of its time doing input-output operations, reading or writing data, versus CPU-bound types of processes. They tend to want to stay longer on the CPU to do some computation, right, and some processing on the CPU. So depending on the process's state, it will be on different types of queues. So we talked about the ready state. If a process is in the ready state, then it will be in a ready queue, which is a linked list that will contain and point to the different PCBs of the processes that are currently in the ready state. If a process is currently waiting for resources, it will be in the waiting queue, which is again a linked list of different PCBs of the processes waiting for some events or for some resources to be allocated. And then the processes keep moving from one state and from one queue to another depending on their current stage of execution and on their current state. So there are also other types of queue, like the interrupt waiting queue, the child termination waiting queue. We'll talk about these later in the course. So when a process or when the CPU decides that now it is time to change the currently executing process and switch to another one, that process is formally called context switching. So it is simply the act of saving the current state of the currently executing process on the CPU and loading the new state of the new process to be executed on the CPU. So it is pure overhead. The operating system is not doing anything useful other than saving the old state and loading the new state. So where do we save that? On the PCB itself. That's where we keep the current state of the process. So this is a simple visual that shows that process P0 is currently executing, and then at some point process P1 has to be executed. So an interrupt is sent, and we do need to save the state of process 0 on PCB 0, and then we need to load the state of process P1 to PCB 1 so that we can remember where the different processes have reached in terms of instructions, and the next time they are loaded, they will just continue executing. They will just check the state and they will check the value of the program counter and just continue where they have left off the last time they've executed. So keep in mind that the CPU state is only up to date when the process is not in the running stage. So currently you can see that process P is not executing, so the CPU state here is up to date. But for process Q, it is currently executing on the CPU, so it is making changes. So the state saved here in the PCB locally is not up to date. So only when we want to switch to another process, then we save the state on PCB Q to make it up to date.